the next ITC colloquium by Hilke Schlichting, and she will speak a little later. She's visiting us from UCLA. Where is Hilke? Over there. We also have as a visitor Gurtina Besla, who will give the Dwarf lecture today. She's getting the Dwarf Prize at the CFA colloquium, and she will also speak at lunch. I should mention that next week I will be on travel to California, so Erwin agreed very graciously to always switch his seat here. And today we'll hear first from David Hernandez from MIT. He will talk about reliable n-body dynamics in astrophysics, implying that most of the things that are done at the ITC are not reliable. Then we'll hear from Hilke Schlichting. She will talk about using ice and dust lines to unveil the surface densities of protoplanetary disks. And then from Gurtina, we'll hear about chemical signatures of population 3 stars in local ultra-faint dwarf galaxies. And finally, from Francesco Belfiore, did I say it right?
Yeah, that's right.
Okay. It sounds Italian. He's visiting us from UC Santa Cruz, and he will talk about how to regulate Quench star formation, insights from the MaNGA survey. Go ahead, David.
Okay, thanks for having me. I'm a graduate student at MIT working with Ed Bertschinger. So I'm going to talk about the n-body problem a little bit. So of course, gravity is scale-free, and it works at all these scales, at the planetary system scale, at the stellar cluster scale, and of course, dark matter halos and galaxies. And of course, all of these problems at 0th order are actually the same mathematical problem, the n-body problem. Now, they have a lot of different features. A stellar cluster is collisional, meaning that close encounters, of course, are important, and the same during some stages of planetary formation. But n is so big for a dark matter halo that that's not important anymore. Close encounters, what was called collisionless, and that simplifies matters a lot for some purposes. But anyway, although they have different features, they're the same problem as 0th order, and we need to solve them. Now, the problem is to understand the dynamics of all these things. N equals 2 has been solved exactly, but no other n is solved. So we have to rely on approximate methods and numerical methods. And of course, we use sometimes numerical integration. So I'm just going to show you a 3-body problem, and I'm going to integrate it with 2 integrators that are quite reliable. This is a movie by Portuguese Schwartz. And what happens is, of course, the red stars are one integrator, the black stars are another, and they become totally indistinguishable, the dynamics after some time. This is, of course, because of exponential divergence, which leads to chaos. And the final state is totally different for the 2 integrators, right? So this, we have to ask, can we trust anything we do, right? I mean, even for a 3-body problem, we can't get correct answers. We can't get answers to agree for 2 integrators. So, why do we trust simulations? I'd like to offer that one possible answer and solution to this problem is what's called geometric integration, named because our trajectories, our phase-space trajectories, are confined very tightly to some geometry. And so if I integrate the solar system with Euler, which is basically what you learn in high school or college, your orbits do totally wrong things. They go outwards and you get unstable solar system. with implicit Euler, you get the opposite behavior. But actually, you can solve this problem when you use what's called a symplectic method. So here's symplectic Euler, and we've solved this problem, and the solar system is stable, at least for a long time. And the same with this, which is also known in astrophysics as leapfrog. Looks great. So I'd like to posit that one possible solution is geometric integration, including symplectic integration, taking advantage of geometries that the differential equations have, the time reversibility of the problem, the energy conservation, so forth, the symmetries of the problem. Of course, it turns out astrophysicists had figured this out a long time ago, and the major codes try to implement this. Gadget for cosmological simulations, symplectic and reversible, and the planetary formations, they try to be symplectic. So symplectic is just a word for our purposes that means Hamiltonian. So actually, you can calculate the Jacobian your code gives, and it's Hamiltonian, it gives special determinant, so forth. So anyway, people figured this out. But the problem is a lot of these are not actually what they claim to be. So I'd like to just present the case of the Mercury code, which is a very popular and successful integrator, and just test a three-body problem, which is a hierarchical three-body problem. And so the Mercury code is used for planetary formation simulations. And so what happens is I tested the symplecticity error, and basically it's something that a number you can form out of the Jacobian, and this code you have to input what's called a switching parameter. And anyway, you can vary this parameter and just take one time step, and you find that for a lot of ranges of this parameter, this code in practice isn't symplectic. So there are cases where this breaks, and it turns out, we want our codes to also be time reversible. So time reversibility, of course, just very simple property. If I integrate with a step and then reverse the velocities or reverse the sign of the time step, I need to exactly recover the initial conditions. And you may ask, well, why do I need to do that if I never integrate backwards? But it turns out that actually really helps the forward dynamics. There's some explanation for this, especially for regular orbits and so forth. So it turns out if you do this, and I should be able to take any arbitrary step size, reverse, and measure an error that's near the machine precision. Now it turns out if you do this with Mercury, you actually not only not get reversibility, you get some error that grows as a power law in time step. And of course what we want is actually these two curves, which is due to an alternative I'll talk about now. And the errors should just be due to round-off error, numerical precision. So of course we need small errors as well, energy errors. So you want it to be Hamiltonian, the code, reversible, and you want a small energy error. So for example, the Runge-Kutta-4 method might give you a relatively small error. It's a pretty precise method, but actually it gives you a large symplecticity error. And what that means is that over the long term with Runge-Kutta-4, that's why you're going to get results that are not accurate. And of course, the Wisdom-Holman method is a popular method which is symplectic, but has a large error, energy error for this problem. So anyway, there are a lot of factors to take into account. You want to obey your symmetries of the problem. So we proposed a way to solve this, and we wrote the n-body problem as a superposition of two-body problems, which was already proposed by Gonsalves, Ferrari et al. But we did this in a symplectic and time reversible way, Hamiltonians and time reversible basically. And when you compute the n-body problem as superposition of two-body problems, it turns out your error is now only due to three-body interactions. So anytime you have close encounters in the code, usually codes have a hard time resolving those, but actually you can eliminate those in this way. You can permit close encounters. This is easy to parallelize because you just have the problem of pairs, and you want to take all the pairs you can take independently and as many groups of those as possible. This is the same thing as a round-robin tournament, trying to get independent groups playing each other. So this parallelizes and can be quite fast. So let me just give you an example where we computed the core radius evolution of a star cluster. And so there are the results. And here are just some very common ways to do this, the Hermite code and some other things. And our method was much faster, taking far superior than Hermite, for example. It's a popular code. So anyway, that's the main idea. And of course, a possible project is, there are a lot of projects. You can calculate dynamics of binaries in star clusters, gravitational wave emission from them, and this sort of code would be very accurate with such a calculation for these sort of predictions. And I'll just leave my conclusions. Thank you for your time. That's right. Yeah. Okay, so what I would say, sure, but can you just take statistics and use some very poor integrator? Like Euler. Let's say I just used Euler and computed a star cluster evolution. Would you believe the statistics even though it's just Euler? And you shouldn't. You shouldn't believe that. So actually, I agree. This is chaotic and you need statistics, but actually if you respect the symmetries of the problem, your statistics will be more accurate as well.
This is a technical question. So you're doing this set of two-body interactions. If you do have close encounters between two of the bodies and you have many others around, the time that you want to consider for those two will be much shorter than if you had wanted to look at the others. So how do you handle the dynamical time scales? Oh yeah, that's great. So part of the problem here is to make a symplectic integrator, typically you need a fixed time step, right? So it would seem, how can I resolve these close encounters if I have a fixed time step? But the solution to this problem, or actually, well, talked with Matt Holman about this a little bit before, but the solution is that actually these two-body interactions are computed with their exact Kepler solutions. And because the period is known, you can actually have a time step. Well, they're usually hyperbolic orbits or mean motion. Your time step can be larger than the dynamical time. And you can still get away with a small error because of that. Yeah. Interesting. Mm-hmm. But I'm not entirely convinced yet. Yeah. It's not perfect, but it's an improvement.
So you showed this image of the millennium simulation in the end, but how is this applicable to cosmological simulations?
Right.
After all, you're working in pairs, and the pairs are still n squared. So
Sorry.
So you said you're doing this for each pair of particles.
Yeah.
So that's still a lot of pairs in the cosmological.
Oh yeah, of course. So this is it's not a problem I've worked on yet, but I'm about to start working on. Yeah, of course, it's a very expensive problem, but there are ways to parallelize it. So in practice, I don't know how that would work out. I haven't tried it yet. So, but I do expect, yeah.
Just in relation to that, I mean, in cosmological simulations, you also have a softening or regularization.
Right.
It seems to be kind of...
That's exactly right. Well, it's a little different too, right? Because you're actually, your particles aren't physical, right? In cosmological simulations, you're sampling, from a fluid and so forth. So there's definitely some subtleties in the cosmological case that need to be thought out a little more.
Okay, so hello everyone. Okay, I need to start with an apology because I'm sorry, I must have had a senile moment yesterday when I prepared this talk on the flight because I prepared a different talk from what I promised Anastasia to talk about, I guess 2 weeks ago. So if you do want to know about disks, do come and find me afterwards, I'll tell you all about it. But somehow, right now, you'll have to listen to me to talking about exoplanets and resonances. So, so the work I would like to tell you about actually was done in collaboration with Margaret Pan at MIT. And basically the question that we were revisiting, and actually I mentioned that very briefly for those who were at the colloquium earlier today, it has to do with understanding the architecture of extrasolar planetary systems. So from Kepler, we have a large number of multiple planet systems, and one of the very simplest things you can do is you can make a histogram showing the period ratio between the planets you have in your system. And so why would you even bother doing any of that? Seems, well, the reason is because many of us expected, because planets are very close into their stars, they're quite massive, bigger than the Earth typically, that maybe many of them are in mean motion resonance. So they have orbital configurations where you have a small integer ratio between their orbital periods. And so when we made this plot, we got this. So let me try to explain this. So basically this black thing is just a histogram, and then these red dashed lines are mean motion resonances, so the dominant one. So this is like the 2-to-1 mean motion resonances, this 3-to-2, 4-to-3, and so on and so forth. And so, of course, we can look at this together, and you should all say, well, I don't see... Well, okay, most planets are not in mean motion resonances, right? It's pretty clear. We don't even need to argue about that. Although there are a few systems that seem... There are a few peaks close to the resonances, but it's really... it's not very impressive. So this, then, is a big puzzle, at least in the sense that we know that many of these planets have hydrogen-helium envelopes, so they must have formed in the presence of the primordial gas disks. Those systems are expected to interact with the disk gravitationally. The torque exchange results in migration, usually inward, but not always. And so inward migration usually leads to very efficient resonant capture and would build nice mean motion resonances. So what's going on here? And so here we sort of revisited this problem of capturing things in resonance and whether the simple intuition that you have is actually correct. So maybe I should, let me, I'll leave it here and then we discuss a little bit more afterwards. So here to set up my problem, we actually have many planets on the disk. So it's not just 2, right? So the multi-planet systems we find, actually 5 or 7. So there are many planets. So it's just having 2 planets is actually an oversimplification. But because for now, just want to tell you about capturing 2 planets in mean motion resonance, I'm just putting 2 planets here for you. And basically, I have an inner planet with mass m1, outer planet with mass m2. And basically, all you need to know is the planet masses is much less than the star. And they're far away they're much closer together than the semi-major axis from the star. And then I have a gas disk with some mass surface density. So the first thing you need to have to capture anything in resonance, you need these things to meet, right? So they need to come close enough that you can satisfy the small integer ratio period. So you need to have convergent migration. And this is satisfied when you have a more massive planet on the outside and a less massive one on the inside. Formation sort of naturally would give you this condition because the type 1 migration rate is proportional to planet mass. And so if the outer one is more massive, it migrates faster than the inner one, it will catch up and you can get capture. So, fine. Then the next thing you need to actually capture anything in resonance is that when the two things meet and you have a chance that you would capture something in resonance, that the time scale that you spend migrating through the resonance is slow enough that basically the libration or the resonance angle can align correctly. So, if I just put down planets on a disk with the right period ratio, they're not automatically in mean motion resonance. The period ratio looks right, but if you look at the system over a longer period of time, you will find that not all of them will be in resonance because to be really in resonance, planets need to meet each other at a certain location in their orbit every time. And so, and you can allow for this alignment to happen if you go slow enough through resonance. So that's why the resonant capture depends on this libration time period. So basically, if I migrate slow enough, I allow for enough time for my orbital kind of meeting points to go through the right sweet spot to result in really resonant capture. Okay? So that's one condition. So the migration time scale has to be slower than this, the time scale for these libration and resonance. And then there's one more condition, and that is that the eccentricities of these planets can't actually be too large. If the eccentricity is too large, it's not that capture can never happen, but the probability to capturing is decreased by this power. So that's sort of the conditions for capturing anything in resonance. So then we started to ask ourselves, what's the typical eccentricity? So what is happening here? Actually, it's not a very difficult dynamics question. We sort of do this question all the time when we think about planet formation because we have many planets steering each other, right, and the disk damping the eccentricities. So basically, we have several planets sitting in the disk that mutually gravitationally excite each other. So that stirs the eccentricity. And then the eccentricities are damped by the gas disk. But because the eccentricity damping time scale from the disk is actually longer than the sonatic time, so the mutual encounter time, basically what happens is on average the eccentricity will grow on a times to a value as much as they can, basically in a random walk, until they meet a time scale that's equivalent to the damping time scale from the disk. And that's sort of the equilibrium you get on average. So this gives us an additional constraint on which systems should be captured in resonance. Okay, and so now we can put all these things together. So the eccentricities we expect are given by the mutual steering of the planets that can basically happen within one damping time scale. And that's roughly what you get. And so now you can ask, is the typical eccentricity smaller or larger than the one you need for a resonant capture? Okay, so now we can output this on a figure, much easier to understand, at least for me, and it's in colors. So here is a plot showing you just the mass of the disk and the mass, basically the mass ratio of the planet to the star, and that's the mass ratio of the disk to the star. And then we can draw various lines on this. So just two different regimes where you have type 1 migration versus just migration due to the Stokes drag. And then this line up there is where the disk mass is equal to the planet's mass, right? You can no longer move the planets with your disks if your planets are more massive than the disk. So that's why there's a cutoff here. And then I just drew here the mass for Jupiter, Neptune, and Earth. So we have some scale that at least I can think of. And then we can ask, so where do we capture planets in resonance? So the first line that I'm drawing here, that's the line that says for which cases is the migration time scale slow enough that I can satisfy it being slower than the libration period. So I can capture these things on resonance. So you get this line here. So everything in this green region, you'd be good. The stuff down here would be moving too fast through the resonance that typically you don't get capture. And then I can put one more constraint, is like which systems have low enough eccentricities that you would capture. So drawing the same line on here, we're left with this. So now the only region where you get efficient capture is this little thing up there. Let's see, maybe is this region up here in green. It's because everything down here, the mutual excitation of the planets is larger than the critical eccentricity for efficient capture. In most cases, these planets will meet, they will go through a mutual resonant configuration, but they will not be captured in resonance. And so this is interesting, because if you look at these values here, so which planets do we expect to be captured? Well, clearly the Jupiters, and planets that are more massive than Neptune, but not below. And this is really interesting, because most Kepler systems have actually masses below Neptune. But we do see very many resonant systems for Jupiters, right? When we have multiple planet systems, they're not very common, but if you have giant planets and multiple planet systems, they're essentially always in resonance. So I need to speed up. We can now look at the real data, right? So the first thing you do is I showed you this plot. So the first cut you can do is put the separated out into light and heavy planets, right? So it's only the ones with the heavy planet on the outside should be the ones that underwent convergent migrations, and if they were captured in resonance, you should still see that. And if you make that cut, and when we know the masses for a subsystem, you actually see the resonance is much more pronounced. So these probably really are just systems where you had the right configuration, and you captured in resonance, and you just stuck in this. And then the ones with a light planet on the outside, the capture may simply not have been efficient. They started off with a heavy one on the outside. They pass through resonance. And then, of course, you end up with the orders flipped, because this guy will catch up, and then you get divergent migration. And then, if you look for the heavy planets on the outside, not only are the resonances more pronounced, you can do a further cut in mass and ask which of those planets have masses bigger than this cutoff of roughly 2 Neptune masses that I showed you. And if you look at this, you see that the planets that are in or very close to these resonant configurations today are really the massive ones, are the ones that are bigger than Neptune. And the lighter ones tend to be the stuff that is outside. So it's not super strong because the statistics are still very poor. But there seems to be some hint in the data that it knows about this. Okay, so I'm out of time. The real way to test this is actually to go around M stars. So where are all the resonant systems? I think this should all be around these M stars. Because for M stars, because of the scaling with the host star mass, planets all the way down to the mass of the Earth should be very efficiently captured in resonance. And so my prediction is that all the resonant chains that we thought we should find in Kepler should be much more pronounced if you look at these multiple planet systems around M stars. And so this is my summary. So where are there are all these resonant pairs, at least for the low mass planets, you know, the terrestrial type, Earth, super mini Neptunes. I think they should be around M stars. And just to remind you that even resonant capture is not automatic, even if you have convergent migration. And so for sufficiently small planets, the mutual excitation in many cases can be large enough to prevent very efficient resonant capture. And that's something we should keep in mind when we look at these systems where we really have more than just 2 planets migrating. So thank you. Yes. I think it does, yes. So that would be a nice example of the M stars, right, and having much more. So my prediction is there should be many more like that. Yes, unfortunately, so there are all these trends there that are consistent, but the statistics are not yet solid that I can say, oh yeah, it for sure has to be that explanation, but it's consistent. Yeah, so I tell you that my prediction is there should be more just like it, and we will get more. So hopefully, you know, you invite me back in a few years, and I can say, I told you, as I told you like 3 years ago.
Questions for the... Looks like everything was clear. That's a compliment.
Well, I think I should have confused everyone because of the previous talk, but let me just say this, because I also talked a little bit about collisions and breaking resonance in my previous talk. I would like to give you the full picture. So the idea is that the instability that can break up resonances doesn't seem to be sufficient to explain why 90% of all systems are in resonance. And what we think we see is that you had inefficient capture that only created resonant chains for, say, 50% of the systems. And then some of those are broken up later due to these dynamical instabilities that I was talking about before. So it's a more complicated thing. And the great thing is we now have good data that we can actually make certain cuts in the resonant pair population to answer questions of the mass dependence and the radius dependence of some of those planets. So we see, for example, a dependence on radius for some of the peaks and missing peaks, which suggests that this imprint of collisions for breaking the resonance where you don't see them and not in the pure resonant population. So that's sort of a, yeah, it's a slightly more complicated story, but I think that's broadly what we see. Anyways, thank you. Yeah, well, I try, you know.
I'm glad you defended where theory works. It's good. Okay, great. So hi everyone, my name is Gurtina Besla. I'm faculty at the University of Arizona, and I'm going to be presenting work that's been led by Myungwon Jian, who is our Theory Prize Fellow at the University of Arizona and soon to be faculty member at Kyunghee University in South Korea. We are hiring again a Steward Theory Fellow, so if you're on the market, please apply for a position. So Myungwon and I have been thinking about whether or not we can really connect the first generation of stars, these so-called POP3 stars, with the chemical abundances that we're seeing in the smallest galaxies that we know of today, which are the ultra-faint dwarf galaxies. These are galaxies with stellar masses less than 10 to the 5 solar masses, or even lower, maybe even a few hundred stars in them. And this is where we're finding some of the most metal-poor stars that we know about. And so it actually hasn't been shown theoretically yet whether or not the abundances that we're seeing in present-day ultra-faints are actually consistent with population 3 yields at early times. So the way we've been tackling this problem is by constructing cosmological zoom simulations of ultra-faint dwarf galaxy analogs. So on the left-hand side, there's a Milky Way type galaxy or halo, and we've picked small halos that are surrounding it, maybe 200 or so megaparsecs away, and we're trying to then, we'll zoom in on them, and this is an example of one of the ultra-faint dwarfs that we've picked with all of its substructure, but this is the dark matter distribution. So what we're going to do now is resimulate this with a zoom using full hydrodynamics, following star formation, reionization, and the added component relative to what other groups have done is that we're going to follow population 3 and population 2 chemical yields and actually follow them all the way to redshift 0. So some of the interesting questions about ultra-faint dwarfs is they've been touted as the so-called relics of reionization. Right? These are believed to have stopped their star formation quite long ago. And the observational evidence for this is abundant. And one of these particular instances of why I really love the local group is that they're nearby galaxies and you can resolve individual galaxies into individual stars. And when you can do that, you can develop color magnitude diagrams like this one, which go to extremely faint limits. And you can determine, for example, the turnoffs of all of your solar populations. So this is a color magnitude diagram using HST data for 6 known ultra-faint dwarf galaxies. This is a very old main sequence and turnoff, and you can estimate from that turnoff what the age of those populations are. And what's interesting is if you take all 6 of these ultra-faints and you account for their distances, their main sequences line up perfectly, which means that there seems to be some global event that stopped star formation about 12 gigayears ago. And the only real mechanism that we know of that would do this for a wide variety of different galaxies at the same time is reionization, right? So this picture sort of is consistent. But what's unclear at this point is whether or not there is a mass threshold, right? A maximal mass below which this process is quite efficient and above which you would still expect these galaxies to retain their gas. So that's one question. The second question that we're interested in is, well, as I mentioned before, chemical abundances. So this is an image here showing you from one of Anna Frebel's papers, the carbon relative to iron ratio and then the iron abundance for a number of different ultra-faint dwarfs. So focus on the red circles. This is from the Bootes 1 dwarf. And you'll notice that there is a carbon-enhanced metal-poor population in addition to a normal carbon population. So there's two populations in these ultrafaints, and the question is, if you actually were to follow the formation of population 3 stars all the way to redshift 0, would we get these two different components? Okay, so those are the two questions we're interested in. And how we're going to do this is we're constructing, as I said, cosmological zooms, throwing in all the physics, and we're going to follow the first stars, which are expected to form at redshifts greater than 15 out of primordial gas. And we're going to then also include their chemical yields as expected from parent stability supernovae and quark collapse supernovae. Then we'll allow for a second generation of stars to form, once again accounting for their chemical signatures. And what we're really expecting is that out of this population that will form out of this gas that has been polluted by these population 3 stars, we may get low mass stars that survive until today. And those are the targets that we're after, and those are the ones that should retain signatures of the chemical yields from these populations. Right? So that's the question. So shortly after that, you'll have multiple episodes of star formation, and you get the first galaxies around redshift 15. At redshifts of 7 to 6, we're going to turn on reionization, which will occur as just enhancing the UV background in our simulations. We ramp it up to a maximal peak at Z of 6, and then we'll follow the resulting galaxy all the way to redshift 0 and really see if we can connect these two populations alongside their chemical yields. So this is a simulation. These are the movies of the simulation of one of our example halos. You're following the dark matter density here, the gas density here, and you'll see in points showing up blue are population 3 stars, and in yellow are population 2. And then here's the temperature. This is going to light up at some point once we hit reionization. And then these are the metals that are being distributed in this process. And our feedback models are very similar to those adopted by the EAGLE simulation, if you're familiar with that. There was reionization, right? So all the gas is ionized at this point, and it can be very difficult for low mass halos to then form stars, right? The idea is that they don't have any neutral gas around after this point, and you can lead to quenching. Okay, so what does the star formation then look like? This is the star formation rate as a function of time. And what I'm showing here are now the starbursts that we're seeing in some of these very low mass ultra-faint dwarf galaxy analogs. And you can see that about at the epoch of reionization, everything basically stops. Now, this quenching is not because of reionization alone, and this dotted line is showing you what would happen if you turned off feedback. So stellar feedback is an important process that is aiding in quenching. Otherwise, these halos would still retain a significant neutral component, which would allow them to continue to form stars. Now, this idea of feedback plus reionization isn't new. This has been around and shown by multiple authors. Onyorbe, Wheeler, and Simpson have shown this quite convincingly. But I think what's different here is we've also looked at a few different halos of slightly higher masses. So these have all got dark matter masses on the order of 2 by 10 to the 9 solar masses. If you bump it up a little bit higher to say 3 or so, or 4 by 10 to the 9 solar masses, all of a sudden these halos are now able to retain gas and have star formation occurring at different episodes at later points in time. What this means is that they're either able to reaccrete gas or they're able to retain enough neutral gas that they can continue forming stars. So there does appear to be a mass threshold, right, below which reionization plus feedback is very efficient at quenching galaxies, but as soon as you go above that, you can retain gas. What's interesting is some of our halos are able to retain upwards to 10 to the 5 solar masses of neutral gas, which is similar to things like Leo P and Leo T, which are gas-rich, very faint dwarfs that have been observed in the outskirts of the local group. Okay, so there does seem to be a mass threshold. And then the next question is with regards to chemical abundances. So on the left-hand side here, I'm showing the carbon relative to iron, similar to the plot that I'd shown from Anna Frebel's work, for one of our ultra-faint dwarf galaxy analogs. And over on the right-hand side is the alpha element abundances. And I can overplot data from the Bootes 1 dwarf from Anna's work, and many other authors as well. So it's a compilation that showed some carbon enhancement as well as a carbon normal population. So what we're finding is that we're able to reproduce the two populations. You have carbon enhanced stars and carbon normal stars, and at the same time you're also enhancing the alpha abundances. So this is the first time that this has been shown that you self-consistently can do this. We're also predicting there to be a metal poor tail that has not been observed. Now whether or not Exactly how many stars you would expect there is not entirely clear because it's a sort of a stochastic process, so you will get a lot of random variations amongst this. But it does seem to be that there is always a much higher, lower metal tail than we're observing today, which is interesting. So, so we're able to reproduce these carbon-enhanced metal-poor stars. We get 2 populations, and this is really from the population 3 component. This wasn't exactly clear at the beginning that, whether or not this whole process would work out in these signatures, and we can show that it does, although there are, of course, other channels for creating carbon-enhanced stars, right? So this is just a proof of concept. Now, we can also say if you really wanted to find population 3 stars relative to population 2 stars, you can look at the other abundances of other elements. So individually, what we're finding is that not only is the carbon enhanced, but so is the silicon, for example, and other alpha elements. So this metal poor tail, for the most part, is exclusively POP3 pollution. It forms this population here. But at the same time, if in here we're showing the blue is the silicon and in red is carbon relative to iron, the abundance of these low metallicity tails seems to have similar levels for the carbon and silicon, whereas the population 2 creates a very distinct distribution between carbon and silicon. So you would actually expect that carbon is not as enhanced relative to silicon from population 2 yields, whereas population 3 yields gives you somewhat similar values. So this is a way to then distinguish a true population 3 signature relative to population 2 or other channels. Right, so in summary, the stellar metallicity, so with regards to stellar metallicity, population 3 stars and the associated external metal enrichment does appear to be important in producing these low metallicity stars, and also for the origin of these carbon-enhanced populations. So you can produce both carbon-enhanced and carbon-normal stars within one galaxy. These population 3 signatures can in fact be distinguished from population 2 based on distinct yield trends, specifically carbon and silicon seem to be similarly enhanced. And I think, in terms of a bigger picture of why this work is interesting and timely right now, LSST, once it comes online, is going to find many more of these things. Right? We do expect many of them. I'll talk more about that later today. And GMT is also going to be able to follow this up with spectroscopy. And this is going to be really, really exciting. Right? Thank you. Yeah, I know, right? Gold star.
It's quite surprising that the 2 are similar in importance because the standard law used to be that supernovae can, just a small number of them can blow the gas out of small galaxies. But is it because the star formation efficiency is so low that therefore supernova driven outflows and so effective?
Right. So that's right. So the question is, why is it a combination of both supernova and feedback and reionization that's important here? And I think part of it is also that there is always residual gas around too, and that gas does come back in, and the gas that's around is sort of diffused relative to where the stars are forming. So you do need to just ionize everything because otherwise stars will just continue to form over time. So I think that really is a twofold process where you're making sure there is no further gas supply essentially for star formation. That's what reionization does. And then you need the feedback to get it out of the really low potential, deep potentials where the density is the highest. So that's why you need both.
In the simulations, do you treat POP3 and POP2 feedback differently?
Yeah. So do we treat POP3 or POP2 feedback differently? So the energetics are based on what we've assumed for the IMF and the mass distribution, and we assume a different IMF for both. So the POP2 is following a Chabrier, and for the population 3, we assume a flat IMF. So you could change the IMF in this, and you would also change the yields, right? So, for example, many people have done more of a top-heavy IMF at early times, in which case you'd get even more carbon than what we're putting here. So if anything, this is a lower limit.
So it does you kind of glossed over this a little bit, but it does look like you're producing more of these very low metallicity stars in the data. Is that hard to get around?
Right. So I think this is an interesting point. So there's this metal poor tail, and we don't see it, right? So is there an issue here, or is there a workaround? So this metal poor tail, I think, is going to be hard to get rid of completely. This is my sense of it. And part of this is we've implemented a metal diffusion scheme. This is an SPH calculations. This is done with Gadget. And so we've had to include mixing of metals in a different way because these are SPH particles. So this diffusion scheme could be too efficient, or maybe it needs to be more efficient. However way this might work out, I'm not entirely sure which way to do it. To prevent metals from distributing too far out, what we're finding is that there's actually star formation occurring in the mini halos before they're accreted, and those mini halos are being enriched by the first population of stars. So sometimes you don't even have a population 3 star go off in a mini halo, but it still forms a pop 2 star that would sit in that metal poor tail. So if you can stop that from happening, then sure, you could probably do that. So there may be some fine tuning there with the diffusion, but I think other codes are, people with different codes are working on this, so we can get a sense there. So my feeling is the answer is in that metal diffusion. So you could actually turn the problem around and say, if we really don't find this metal poor tail, there may be a way to tune our models better to understand this.
There is a simpler solution to this, which is that the mass function of stars is such that make mostly massive stars below some metallism. And those massive stars are not around anymore. So if your IMF does not have low mass stars and low metallicities, then you don't see those stars.
Right. So this low metallicity tail, though, where that's coming from is from the next generation down from the POP3. So
those stars are mostly
yeah.
massive.
Oh, I see. Right, yeah, that's right. Yeah, so for that second generation.
We see that in our galaxy.
Yeah.
You know, the stars that middle port do exist.
How poor are we talking?
Minus 4, some stars exist in the galaxy.
Right, so
Number of them you're saying.
yeah. So exactly. And so, and then plus we're also saying that there should be some down to -6 or -5. And so this is, and it's just not clear to me right now whether or not the observations are there to really definitively say one way or the other. But at the same time, I think there may be something in our models too that can be better understood. But overall, I thought this stuff was pretty awesome because I haven't seen this before at all. And it's finally a way that theorists can really start to reach across to observers in terms of the chemistry for these things. Yeah. Right. That's a good question. So the question is, have we learned anything about POP3 yields? Well, I've learned that the kind of general lore of what's being accepted in that community seems to work out pretty well. And in some other cases, we found much higher carbon enhancements than others. And again, in terms of how many that are in the metal poor yield, that area also is very stochastic. So right now we have 2, I think, low numbers of these things having been simulated at this point. So I don't have a complete answer to that. I think there is a lot of wiggle room in what you put in there, though. So I don't think we've made any real constraints on that, to my knowledge. Mm-hmm.
I seem to have randomly added a slide. All right. That's what happens when you have too many dongles and touch the wrong thing on your computer. All right, let's hope that's it. All right. Okay, so thank you very much for having me here. My name is Francesco Belfiore. I've recently moved from the other Cambridge to the University of California, Santa Cruz. And it's great to be back in a weather which really reminds me of the UK in a place similarly named. So I really feel at home here. So what I want to do today is give you an observational perspective about the quenching of star formation in galaxies. And in particular, I want to take... I knew the dongle was going to do that on me. And there doesn't seem to be anything I can do about it. So I'll just continue, and if it flickers, ignore it. Okay, so I want to tell you a little bit about quenching and about how we can study that with results spectroscopy. So let me define my terms first. You're probably all familiar with the idea of a star formation main sequence. So it's this relation between star formation rate and stellar mass. which is followed by star-forming galaxies. This is a nice correlation. And then, this population of galaxies in the local universe is strongly bimodal. So you have this other peak of passive red sequence galaxies. This has been known for a long time, you might argue, since the time of Hubble, although large-scale spectroscopic surveys of the nearby universe, like Sloan, have been instrumental in really defining this picture in the local universe. Some fundamental open questions remain about what drives the physics of this bimodality. In particular, I'm going to refer to as quenching, to whatever process drives galaxies from this star-forming sequence to the passive population, without necessarily implying that this is a fast process. And really, there's two very important questions that we've been trying to address. One of them is the physics of this process. There's a number of very reliable and possibly happening all at once reasons why you'd get quenching of star formation. There's certainly something related to the halo, and so you might get a shutdown of accretion. There's also environmental processes that might be especially relevant in the low redshift universe. The effect of AGN has more recently been studied in more detail, and in particular the effect of AGN at expelling gas from galaxies and how that might lead to quenching. There's also interesting links to the structural properties of galaxies. So you might think as the galaxies grow a bulge in the central regions, that might stabilize the star-forming disk and eventually lead to a lower efficiency of star formation or perhaps overall quenching of the galaxy. Now, the reason why I feel like I have to defend or somehow define the word quenching is that it's somewhat misleading if this process is not fast. If you imagine the process to be fast, then quenching just drives galaxies down on a and maybe this word is somewhat motivated. But on the other hand, there might be evidence for this process, especially at redshift 0, to be very slow. And so whether you're talking about secular evolution or quenching becomes a matter of linguistics more than of physics. So we do know one thing about quenching, and that's that it's strongly correlated with the structural properties of galaxies. So for example, if you color code galaxies in the star formation rate stellar mass plane by their Sirsic index, which is just telling you how much the light is concentrated, we do know that passive galaxies, but also galaxies in this transition region between the star-forming and the passive populations are more concentrated. Oh, I'm sorry, this is annoying. They have higher Sirsic indices, they have larger bulges or larger bulge-to-disk ratios. So there's clearly an interesting relation there. This has been very well studied, but it is difficult to study with photometry. So for example, in this particular work, Fang looked at the photometry from Sloan and tried to derive stellar masses from that, and came to the conclusion that if you derive stellar mass profiles for blue, green, and red galaxies, it will come back in a moment, I'm sure. I actually don't have this. I know, it's Mac. I don't have anything that can plug into this, I'm sorry. However, while deriving stellar mass profiles is probably reliable from photometry, and here you clearly see that the Green Valley galaxies might just be blue disks with a larger bulge, it is very difficult to trace star formation in galaxies at redshift 0, especially with photometric colors, because you're sensitive to the effects of dust and of the underlying stellar population. So what you really want is to have spectroscopy like Sloan, but instead of just looking at the central fiber or having one spectroscopic element per galaxy, you want to do this in a specially resolved fashion. And in particular, the question I'd like to address today is, based on this sort of data, are these transition galaxies, these Green Valley galaxies that lie between the red and the blue population, just blue disks with larger red bulges, or is there different physics going on? So the solution to this problem from an observational point of view is that you take the Sloan 2.5 meter telescope, and instead of drilling thousands of holes in aluminum plates and plugging fibers in them, you bundle the fibers together and build integral field units. Oh, wow. That's beautiful. Okay. So this is what we're doing for the MaNGA survey. also known as MaNGA, whatever. And we are doing a survey of about 10,000 nearby galaxies. We have IFUs of different sizes that are optimized so that we can cover the largest amount of galaxies that are still representative of the populations of galaxies in the nearby universe. I don't have time to tell you more about the survey. We cover basically a representative sample of galaxies of stellar mass larger than 10 to the 9 in the local universe. I just wanted to show you some data. So for example, these are some of our real targets. You can see the hexagons, which corresponds to the size of our IFUs, and these are maps of the H-alpha emission line of exactly the same galaxies. And I mean, I don't have time to scroll backwards and forwards, but you can see that there's a lot of structure in these maps. So I'm going to tell you just one thing about the spectroscopy, which I think is really cool, and that using spectroscopic line ratios, you can start to study where star formation happens in galaxies, and in particular, by using standard diagnostic diagrams, you can tell whether the line emission that you see is actually due to young OB stars, so these are really H2 regions, or on the other hand is excitation due to hot evolved stars, which for a long time have been, ionization of this type is generally referred to as LINER. In my work, I argue this is more correctly called LIAR because this is not necessarily nuclear emission and we shouldn't confuse that with AGN. But basically what MaNGA is really good at is trying to map that transition between the star-forming regions, which we don't resolve because we have kiloparsec resolution, and the regions in galaxies where there's no star formation going on. And in particular, you have this interesting type of galaxies in which the disk is star-forming, but the central regions are not forming stars anymore. So I'm going to call these centrally quiescent galaxies, and maybe we can see where they lie in the color magnitude diagram. Usually if I step back, it comes back. Well, maybe not. All right. Okay, I'm going to pretend the slide is up there. I'm going to tell you that the centrally quiescent galaxies actually, unsurprisingly, lie in the Green Valley because they have central regions which are not forming stars anymore and are red, and blue star-forming disks. If somebody else has an HDMI to USB-C converter, yeah, I know. Can do, but at this stage I have like 4 slides left, and it seems I can. All right, let me use the board. I don't know how to get rid of the screen though. So, I mean, the last thing I wanted to show is using our MaNGA data, and so our maps of the H-alpha surface brightness, we can correct for dust in a meaningful way by looking at line ratios, for example, between using the Balmer decrement and, of course, it's bound to be like that, isn't it? You're just making fun of me today. Anyway, what I really wanted to show you is the final, I guess. Right, okay. So these are profiles of specific star formation rates. So star formation rate divided by star mass. And I'm looking at galaxies in different mass bins, so going all the way from 10 to the 9 to 10 to the 11.5. And I've divided the sample in galaxies that lie in the blue cloud and on the green valley. And there's 2 interesting features in this plot. One of them is that as you move to higher masses, you start building up the bulge, which leads to a strong suppression of the specific star formation rate at the center. I will take 1 more minute. And then the fact that, which I think is even more interesting, that in the disks of blue cloud and green valley galaxies, the specific star formation rate is suppressed in the green valley with respect to the blue cloud at all radii that we can probe with this data. So to some extent, my conclusion from this is that in order to be green, you can't just have a large bulge, but you also have a fading disk, which is an interesting physical statement to what is happening in these galaxies. The last thing I wanted to show you is what happens if you draw the profiles only of the galaxies that have no star formation in the center, so these centrally quiescent galaxies, for which I was trying to show you a map earlier. And my first question was, okay, these are just galaxies that have the largest bulges. Unfortunately, it's not as simple. So if you take galaxies that have star formation in the center, but with the same bulge, or with the same stellar mass surface density within the inner couple of kiloparsecs, then these are the profiles you get. So they are substantially different, even a larger radii. So it's not as simple to say that the galaxies with centrally quiescent regions are the ones with the largest bulges. So this is my summary, in the sense that the centrally quiescent galaxies have both quiescent bulges, but also disks with lower specific star formation rates. And I think this ties in very beautifully with a lot of the very exciting work that's been done by people, including Sandro and others with 3D HST, on how the populations of galaxies at high redshift look like. And what gets me very excited is that you can start to do result spectroscopy of high redshift galaxies and look for similar trends as the universe was younger and really trace the emergence of this quenching process. So I'm just going to leave you with my conclusions. It takes more than a large bulge to be green, and the green valley is not just red bulges in the center, but it's also fading disk, a disk with star formation being suppressed at all radii. And to me, this is strongly indicative of a slow quenching scenario, and it fits very well with the idea that the gas is slowly being used up in star formation, perhaps not being replenished, as opposed to an ejective scenario that would lead to a fast quenching timescale. Thank you so much, and sorry for the technical problems. I should have kept.
Make sure that we have the correct connectors for other speakers. Sorry that we didn't. Questions from Francesco? Rosanna?
I was interested in your moving from the liner to the liar, because one of the things that I've wondered about for a while is the role that X-ray binaries, for example, have in producing some of the very same effects that people have been associated with liners.
That's right.
Because, you know, after sometimes a few times 10 to the 6 or a few times 10 to the 8 years, you end up with a very significant population that's not only X-ray active, but that also is capable of a great deal of ionization. And so I'm wondering, you know, would that perhaps lead to this sort of slower, it's not just that you're running out of gas, although that I'm sure plays a role as well, but that the population itself is kind of spreading out and doing a very good job of ionization.
That's an even more interesting point than, you know, just looking for the source of the ionization of the gas, and that's certainly something that some people have thought about. I can tell that when you look at the ionization for these liners or liars, the general consensus is that most of the energy comes from hot evolved stars, and X-ray binaries are only a fraction of the ionization that you'd get from the hot evolved stars. But there are significant uncertainties in our modeling of this stage of star evolution, and there's still some tension between the observations of these stages of stellar evolution in our models. So it's really something that we should work on more if we want to pin it down better.
We got to our time limit. Thank you.
It's my fault. I thought. Now I'm speaking to everyone. Sorry about that. No, this is what happened.